All right, we left off talking about the first way that the nature of the reactants actually affect the rate of a reaction would be different allotropes, different versions of the same element. White phosphorus, you saw what it does. But I kind of mentioned to you that some of the places we use it. We talked about some of the places we use white phosphorus. What were some of those things that you used in? Tracer bullets, and I told you to ignite napalm. It's used. Because white phosphorus, when exposed to air, just automatically catches fire. So I have a couple of neat little video clips of both of those things if you want to watch them here. And music. Remember, not every bullet is actually a tracer bullet, so imagine how many bullets are being fired. I figured the guys would like this to get the bull crap up. That's pretty amazing. Yeah. All right, that's enough of that. Now, this is actually a Vietnam bombing run, stock footage from Vietnam. And again, you'll notice before the napalm's ignited, you'll these white sparks. See the white? That's the phosphorus igniting the napalm, and then it's basically catching everything on all the napalm on fire. Pretty neat.
Yeah, I remember now.
Yeah. This is I knew both would like this.
I was hard. I was flying a helicopter right now.
Yeah. Actually, this is probably not a helicopter. He didn't do bombing runs from helicopters. But
I watched it.
It is see the white stuff that's igniting that's stuff that lights it on fire, and the napalm stuff that actually burns.
Yeah, you're gonna burn the forest down there.
Yeah, seriously, that's what they did. The reason because the forest was such a great cover, they would have to do that.
Now we know why it's global warming.
Exactly, all that napalm.
Because Al Gore told them.
All right, so that finishes up what we were talking about with the different allotropes. White phosphorus being a much faster reaction than red phosphorus. Just exposed to air and it catches on fire. Hit that light back. No, hit the light back. I have another one actually I found that's coming up in a minute on the next thing, which, by the way, still under nature reactions. In your notes, if you're taking these notes, we're still under nature reactions number 2, subdivisions. 1 was allotropes. 2 was subdivisions. And there's going to be a third one. All of them are just under the first one, nature of the reactants. They're not like 1, 2, 3, and there's only one more left. I told you there are 4 major factors. These are all of the same one. How I could change the actual nature of the reactants without actually adding energy to them or anything like that. So subdivisions is a good way. And, of course, another way you're used to talking about that is surface area. And watch little sparkles. It's like more surface area. That's right. Now, another little video clip for this. This is a news program did this. I actually bought the kit to do these. It has to do with like a grain elevator explosion. Those of you who maybe are farmers know that if you store grain, even anything, pretty much that if on a dry day would cause a lot of dust in the air, you have to be careful because smallest spark can actually set the stuff on fire. You think to yourself, well, geez, it's just corn or it's just some kind of wheat or grain. How flammable can it be? And it's not really flammable. If I put a match up to a kernel of corn or even a kernel of wheat, it's not going to catch on fire. However, the dust from it, because of the surface area being so high, is extremely flammable, as I'll show you with this little demo here. Turn that light off again.
In Thursday means it is time for Imagination Station. They are visiting us here on WTO11 New York Day. Frostology is going on at the Imagination.
And so what I'm going to do is I'm going to put a little bit down here.
This is just a powder, like baby powder almost.
What I want you to do, this is a very flammable substance. All right, so let's go ahead and get your goggles on. Just the goggles.
Just the goggles this time. Safety first.
Well, it's not. It's like the consistency
go ahead and touch it to my powder there.
And nothing happens. Because
nothing's really happening.
It's just sitting there.
It's
It's not a lot of surface area.
But the thing is all that powder is laying really flat on the ground.
Okay.
And one component you need to make a combustion reaction is oxygen.
All right.
So I like to think about it, I have more oxygen surrounding me if I jump in the air than if I'm laying flat on the ground.
Okay.
Right? That kind of makes sense.
Makes sense.
So in order to get this in the air, I'm going to actually kind of spray it in the air,
Okay.
get some fine powder. And what I want you to do is I want you to take this blowtorch, hold it out in front of you, tilt it towards me a little bit, and just hold it down.
Okay.
All right? So go ahead, give it a light, and I'm going to go ahead and put this right through the air. And now that it's surrounded by more oxygen, we're
See how
able to get
surface
a
area
lot
makes
more
a huge difference.
of that combustion reaction.
But
Kind of cool?
the thing I used to have
Yes, very cool. So this is actually kind of a
going to
big
do
worry
here
for
is
us
what's
because
called the
we're
grain
short
elevator
staffed.
explosion.
This is actually kind of a big worry. It's okay, Chris.
Okay. I'll set it down for now.
This is actually kind of a big worry for certain companies, factories, that say a sawmill or maybe a factory that makes baby powder, that there's all this flammable material that could be floating around in the air.
Okay.
And it might only take one little ignition point to let it all go off.
Okay.
So what we have is, what we're going to do is, I've got this kind of miniature model of an elevator. So this isn't a paint can anymore, it's an elevator.
All right.
And
I'm using my imagination. This should work just fine.
So they have, for those big grain mills that you see, kind of like out in the country, they actually have an elevator up there that takes the grain to the top. And so this is something to kind of say, what if all those grains are in the air? Okay. And there was a slight, maybe a broken outlet or something like that. And we're going to go ahead and test that. So inside of here, I have a small funnel. And that funnel is going to hold some of my powder here. And then I'm going to have a candle down in there. And when you squeeze this, it's going to launch. You can see I already have some powder.
This first time it doesn't work. I'm going to
never know. You never know when something's going to go off or not go off. Okay.
So this one doesn't work. So here's the one that does.
And I'll put this one right underneath. As you said, sometimes that funnel, that powder will come up and it will actually blow out the candle, and we don't want that to happen. So, are you ready? Don't do it yet. Go ahead. Excellent. There we go.
All right, so that's basically falling over. That's like I said, I bought the kit to do that with the paint can and the powder and all that stuff, and I tried it, and it's like, honestly, got once out of every 5 times it actually worked. So it really wasn't worth doing it. It was a real pain in the neck. You know how some of my demos I've done in the fume hood, it takes me forever to get them to work. That was one that was just not worth it, because half the time when you squeeze the powder in there, it would just blow the candle out. All right, it had to go above it and be enough to actually ignite it. And, it was just a pain in the neck. So I thought I'd just show it to you. All right, so that's surface area or subdivisions. Next, number 3. Solution in water. See, water. Did you watch again? Watch. It's solution in water. See, it's like watery, like waves. Yeah.
This is like number 3 underneath A.
Yes. All of A is what? Nature of the reactants. That's what I was trying to tell you before. All right. Solution in water. How's that going to? By the way, every one of these has a reason. I can relate back to my 2 theories, collision theory and transition state theory. Let's think about the collision theory. All right, there are 2 parts of the collision theory. You had to have enough energy, and you had to hit in the right orientation. When it comes to energy, putting the guy in water is not adding any energy to it. Neither is powdering him. It's just giving it a better chance of hitting in the right orientation. You get more chance for those in this case of the combustion reaction, more chance for the oxygen molecules to hit those grains of flammable substance, whatever it is. All right. Same thing's true with water. Most of the time we're going to do our reaction. We're going to do a lab in about a half an hour after I'm done with these notes. The lab back there, every chemical you're using is already in solution. We use cobalt, nitrate, and bleach to make gas, oxygen. And when you do that, I don't want to take solid cobalt nitrate. I have that in the back. All right. I don't want to add that. I don't want to add to well, you don't have solid sodium hypochlorite, but bleach. But basically, almost everything you use in my lab is a solution. It's a bottle. It's in water, because it creates a better chance of an effective collision with the right orientation. If I just put 2 solids together and mix them up, it's not going to react as fast. But if I dissolve them both in water first, they're going to react almost immediately.
Why is sodium hydroxide a pellet?
It is a pellet, but most of the time when you use sodium hydroxide, we're using it in. I'm having you usually dissolve it in water first, and then we add it to something. Almost, and that's the crazy part about most. I think I have to get this. I have to say this multiple times throughout the year. A lot of times, like almost every one of you guys thinks, for example, that hydrochloric acid is a liquid. HCl, hydrogen chloride, is a liquid. It's not. It's a gas. It's a gas dissolved in water. And so what you're pouring in there is it's like ammonia is the same thing. Ammonia is a gas. But it's when you're I buy a bottle of ammonia. No, you buy a solution of ammonia. You buy a solution of hydrochloric acid. There are not, and salt. You can think of it with salt water. Everyone knows salt's not liquid. Salt water is a solution of salt water. Same thing with sugar water. All right, so we put things in water to make them have a better chance of a reaction, have it faster. That's all of those together combined to make the first thing. Second thing, that's going to make. Oh, look! See, it's red. Temperature. Yeah, I can heat them up. Obviously, the way this guy's going to work is he's actually going to be giving him more energy, giving more energy to the reaction. So we can relate this to the transition state theory instead of the collision theory. It's a little bit easier to see it that way. Let me show you. All right, remember these, don't draw these. Remember these two graphs, okay? All right, let's do a little bit of review while we talk about them. Which graph is that? Exothermic, it's releasing energy, right? Starts high, ends up low. Endothermic here. Now, one way we can get this guy to work faster is just by giving him energy, pushing him up that hill. That's what temperature does. It's very simple. So I would say the transition state theory explains this one pretty well, whereas the collision theory, not necessarily getting any better chance of an effective collision based on its orientation, although since it's moving faster, it's going to hit more often. It's mainly about energy. All right, it's giving these guys more energy. Okay. What the heck? Nice. That's good. All right. Stupid thing. Okay. Don't know why I did that. What did I do different? I mean, I just hit the board.
Yeah.
Maybe you wait because you went to an expo yesterday.
Yeah, maybe.
Maybe. Anyway, energy. They all have energy because they're spinning around like that. Increasing temperature increases the kinetic energy of the particles. So obviously you're just pushing them over the hill. There is also the better chance of them hitting each other since they're moving around faster. And that's what the collision theory says too. Now what we're going to test in our lab today, because we have a double period, what we're going to test in lab is this next little rule of thumb. All right? That I'm going to give you here. Turns out that in general, and this is by no means a hard and fast rule, all right, and your percent errors are going to be somewhere around 10 to 20% when you do this lab today. It's not going to be like a really accurate. Like in the thermodynamics, our percent errors were very good. Remember the labs we did with the first law? I mean, it was like less than 5% error for everybody. So even zero. Somebody had zero. This guy is not going to be, because basically here's the rule. The rule simply says the rate of the reaction doubles approximately with every 10-degree rise in temperature. Now, that's not by any means perfect, but you will be able to test that. And certainly you're going to see in the lab that the rate's going to be faster when we warm it up, and that's exactly what we're going to do. All right, so it rises. I mean, it increases with about every 10 degrees Celsius rise, by about doubles. All right. So that's the second thing. So we have the nature of the reactants. We can change all those things about it to give a better chance of an effective collision. We can give them energy to have a better chance of an effective collision. And the next one, and this is a biggie, all right, is the catalyst. We're going to talk about him. All right, how a catalyst works. Now, I actually have a job for you. If you're done with that lab early today, you're going to have time to start on this. And I think you will be done with the lab early today. Their class got finished, and I was able to show them the videos that I showed you. They didn't get them yesterday either. So you should have about 15 minutes at the end of the period to look up stuff that you're going to do on your own. Remember, every chapter from now on, I'm going to try to find one section that you're going to do on your own. This is the one section. It's going to have to do a specific type of catalyst. But let's talk, first of all, how normal catalysts work, okay? We all know that it lowers the activation energy. We saw that from the first week of Chem 1. I did a lab or a demo on that, and I gave you these same graphs. You'll probably remember. Endo and exothermic. I talked about how it basically lowers the activation. I would like you to copy this down and illustrate or identifying the two different things here. This is the catalyzed reaction, and this is the non-catalyzed reaction, right? Okay, make sure you draw these two things. What happens is you're lowering the activation energy. So this is with the catalyst, and this is without. It lowers the activation. It makes the hill lower. It's easier for him to get from point A to point B, from the reactants to the products. Oops.
Whoa, yeah, hold on there.
Yeah, I thought it was going to have the bottom number, or the bottom axis should be time. Okay. So the difference with the catalyst is the activation energy is going to be a little bit lower, and therefore the reaction go a lot faster. Now, you may remember the demo I did for this one back in Chem 1. That was the one where I took hydrogen peroxide, and I added into a big beaker, okay, and I put in a catalyst, and the whole thing foamed up really fast. Hydrogen peroxide is always breaking down. It's always if you leave it in a clear bottle in your cupboard for a couple of years, you're going to have a bottle of water. It's always breaking down. But I can make it go faster by adding potassium iodide. I could also add blood. You've seen what happens when hydrogen peroxide hits your blood. It fizzes. And that's exactly what happened. I put a little soap in there, and it all happened very quickly. So I took away some of the activation energy. All right? So that's how a catalyst works. However, we're going to go a little further. It's Chem 2. You're going to be doing a couple of different things on your own. One is, I'm going to talk about, that's pretty cool. I'm going to talk about biological catalysts a little bit. And then I'm going to talk about homogeneous and heterogeneous catalysts. Now, let's first talk about biological catalysts. I want to refresh this with you because we've done a lot of, you can almost call some of this class biochem. First of all, organic is a lot of biochem, all right, with all the stuff we're doing with alcohols, carboxylic acid, esters. They're all stuff you would see in biochem anyway. Then I went further and did the stuff on polymers. We did a whole big long thing on proteins and DNA and transcription and translation. Well, here's our last time we're going to see biology, probably this year. All right, and it has to do with catalysts. You may have seen the lock and key mechanism. Remember this?
Oh, yeah.
All right, it's pretty easy. All right, let's watch what happens in this. Turn the light off. You can probably see it a little bit better. You don't have to draw this. I just want you. You don't have to draw this. You just have to watch it. Turn it off. All right, so I've got your enzyme here, and this is these shapes and these structures basically mean something. All right, remember orientation was a big deal. You need these two guys. Let's call him A and B. We need A and B to get together. And the only way they're going to get together in your body or in that beaker is if they hit in just the right way. See how this guy's going to fit right into there? Well, the odds of that happening just hanging out in a beaker aren't that good. So the reaction doesn't happen that quickly. But you get an enzyme added in there. How does that lock and key mechanism work? Well, basically, this enzyme probably has some charges here, maybe negative charges here. This guy's got positive charges there. So he's going to attract him to that spot. And this guy is going to attract him to that spot for the same reason. And once they get together, now they're in the perfect orientation. And they've formed this new compound. Once that new compound's formed, there's usually some kind of morphological change, such that this guy now breaks off, all right, because it breaks away from these binding sites that were attracting them a little while ago. And the new product is formed. He goes off and does his job. This guy goes out and looks for more A and more B. And that's the whole basic system behind this method. The lock and key mechanism. Okay, that's what it's called, lock and key model. You can put the light back on so you can see better. Thank you. All right, so the lock and key model basically says enzymes bring the substrates or the reactants together into the proper orientation, and they generally weaken those bonds so that they can actually form these new bonds together. Now, by the way, this also illustrates another nice part about catalysts. Catalysts, by definition, are not used up in the process. A little bit of catalyst goes a long way. I don't actually have to keep adding more catalysts or adding more energy like you would have to add to heat something up. A little bit of catalyst can be used over and over and over again. All right, so once that new thing is formed, once the substrates are formed, a product, the new thing breaks off, the new compound breaks off, and the product is released, leaving the enzyme free to go pick up some more of the substrates, the reactants. All right. Oops. Now, part of this I told you is going to be done on your own, and I'm going to start you off on that road here in a second. I'm going to classify catalysts into two different kinds besides the biological ones. There's two different kinds of chemical catalysts. All right, I can have homogeneous catalysts or heterogeneous. They both work by lowering the activation energy. Both major reactions happen faster. They both are not used up in the process. However, they work a little bit differently. I'm going to do homogeneous for you. You are going to do heterogeneous for me. And you're going to have to read about 2 or 3 pages in your book that are going to explain you the 4 stages in particular of how your catalytic converter in your car works. Everybody's car has a catalytic converter. You've probably heard that term before. And what it does in the car, I want you to read about and to be able to explain. There are 4 stages of that heterogeneous catalyst. But let's talk about the homogeneous one first. Homogeneous catalysts exist in the same phase as the reactants. That time I did the foam one, where I added a solution to another solution, that's a homogeneous catalyst. They're both liquids added to another liquid, and basically they're reacting in the same phase. And they work the same way same way you would think of a catalyst to work. It forms a lower energy intermediate. You don't know what intermediates are really yet. We're going to talk about it in this chapter. There's different ways sometimes to make a reaction. Oh, yeah, you kind of do know about intermediates a little bit. Remember in the mechanisms for electrophilic additions, nucleophilic substitution, you formed, there were some of them were like 2 or 3 steps, some of them were 6 or 7 steps for the free radical halogenation. Well, if you can form, if a catalyst is added, sometimes those middle steps in there will be easier to do. And that's how it works, by making the intermediate steps easier to, your final product is the same, but you can actually go through a different series of steps maybe, or lower the energy required to do those same steps. So that's how a homogeneous catalyst works, all right? A heterogeneous catalyst is one you're going to have to do on your own after I give you a little brief introduction here. Especially, you're specifically doing a catalytic converter, actually. Works differently. It's not in the same phase. I'm not adding a chemical to a chemical. I'm basically usually giving it a surface upon which this reaction can take place. Remember underneath how many of those arrows was there platinum, nickel, different catalysts that were in there, iron, all right? A lot of those guys were there. You didn't realize at the time. You just, when you were doing the organic reactions, those little things underneath the signs, those little catalysts written underneath the signs, were just a metal added to allow a surface upon which this reaction could take place. Okay? They are not in the same phase as the reactants. It's not like I added a chemical to it and had it forming a different intermediate or something. But rather, I'm just giving it a surface that makes it a little bit easier for these guys to get together. And I'll show you how with one example in a minute. Okay? They will offer a surface upon which the reaction can occur. Remember the water decomposition one. I had I never really showed it to you close up. Maybe I should have at one point or another. In Chem 1, we did decomposition reactions, and I had a tube here and a tube here, and they both have bubbles coming up, and I divided water into hydrogen and oxygen. Well, if you were to have looked closely, the bottom of each of those tubes, there was a flat platinum piece of metal there, where all the bubbles were coming off of. That was the surface upon which the reaction was taking place. Okay? Let me show you this. Take this reaction here. Don't have to copy it, so always watch this. Say I'm taking this reaction. I'm going to hydrogenate an alkene. We've seen that reaction, and it had platinum or nickel as a catalyst in there. You had to write that down somewhere along the line over the course of organic. Here's what's really going on in that reaction. Let me show you. Okay? Here's your metal surface, right? What happens is that metal surface attracts the hydrogen atoms, which it can break up then into individual atoms instead of being hydrogen diatomically bound together really tight. Along will come an ethylene molecule, all right, and it will pick these guys up. Remember doing that alkene thing on the going through the computer series of cards, almost like each one of those. One of them was it showed this exact reaction. It was hydrogenation of an alkene, and it asked you the question. You may remember it asking you: are the hydrogens added cis or trans? Remember? And it did add them cis because it's picking them up from the same side with the catalyst on there. Okay, so it would come down here. It picks up two hydrogens and then it leaves. That's basically the function of a heterogeneous catalyst, just to be a surface upon which these things can happen. Now, this is going to be applied. You don't have to copy that down because you're going to do a specific example. That's an example I could have used. But I want you to read about 3 pages worth of an example on the catalytic converter, how in your car a catalytic converter works. You guys, I believe, what edition do you have? Look at your book there. 6th or 4th? Which is it? Tom, quick. It's right on the front. It's right on the front.
6.
Okay, so write these page numbers down. 690 to 692. It's only 3 pages. And you want to make sure you take your notes on the 4 different stages. There are 4 stages. I'm going to just write that down so you make sure you have that, because that's what I'm asking on a test. 4 stages of the catalytic converter. Make sure you have your own notes on that for the test. Guaranteed 10-point question on the test. Last question on the test, I can visualize the test in my head right now. It will say, describe in as much detail as possible how a catalytic converter in your car works. And that's what you'll have to do.